So we have physics Ph.D. qualifying exam practice problem number 28, quantum mechanics domain. So let's begin. A two-level system evolves under the Hamiltonian H equals h bar omega over 2, sigma sub z. That's the Pauli z, and interacts weakly with an environment obeying the equation d rho dt equals negative I over h bar, a commutator of h and rho, plus gamma, and then we have parentheses sigma minus rho. Let me start that again. Plus gamma, parentheses sigma minus rho, sigma plus minus 1/2, and then we have the anti-commutator of sigma plus sigma minus rho. Okay. Part A, show that the trace is conserved. Part B, derive the coupled differential equations for the matrix elements of rho. Part C, solve for rho of t assuming arbitrary initial conditions. Part D, determine the long-time equilibrium state. And Part E, compute the von Neumann entropy as a function of time. So this is a density matrix and open quantum systems problem. So for just prerequisite, we have what we were given up here, and now we're going to let rho equal this matrix here. First row is rho sub EE, rho sub EG. Second row, rho sub GE, rho sub GG. Okay, where ket E is the excited state and ket G is the ground state. So for part A here, for the trace conservation, Hamiltonian part satisfies this. The trace of the commutator of H and rho equals 0. And for the dissipator, the trace here, sigma minus rho, sigma plus, that equals a trace sigma plus sigma minus rho. So we have the trace here, bracket sigma minus rho, sigma plus minus 1/2 the anti-commutator, sigma plus sigma minus rho. That equals the trace of sigma plus sigma minus rho minus the trace of sigma plus sigma minus rho, and that equals 0. So ddt trace rho, that equals 0. Okay, so that is part A. Now for part B, derive the coupled differential equations for the matrix elements of rho. So here, so let me just adjust this. So for part B, here, matrix elements equations. We have here this sigma plus sigma minus. That's going to equal this ket E bra E. And the master equation gives this. For the following, we have this P dot sub EE equals negative gamma P sub EE. And then we have P double dot sub GG, and that equals plus gamma P sub EE. P dot sub EG equals negative parentheses I omega plus gamma over 2, close parentheses, rho E sub G, and then rho sub GE dot equals parentheses I omega minus gamma over 2, close parentheses, rho sub GE. And pardon me if I mispronounced anything there, sorry. Part C, they want us to solve for rho of t assuming arbitrary initial conditions. So for part C, the general solution solving each equation, rho sub EE of t equals rho sub EE of 0, E the negative gamma t, rho sub GG of t equals 1 minus rho sub EE 0, E to the negative gamma t. And assuming trace rho equals 1, the coherences are rho sub EG of t equals rho sub EG of 0, e to the negative I omega t times e to the negative gamma t divided by 2. And then here, rho sub GE of t equals rho sub GE of 0 e to the I omega t times e to the gamma t over 2. And then we wind up with this matrix here. So rho of t equals, following for the first row, you have rho sub EE of 0 e to the negative gamma t, rho to the E sub EG of 0 e to the negative I gamma t, an I omega, sorry about that, I omega t e to the negative gamma t over 2. So that's a negative gamma t over 2 there. And then here, second row here, rho sub g e of 0 e to the I omega t times e to the negative gamma t over 2, 1 minus rho sub EE of 0 e to the negative gamma t. And that was solving for rho of t, assuming arbitrary initial conditions for letter C. Now for letter D, they want us to determine the long-time equilibrium state. So the long-time equilibrium state here, as t approaches 0, we have rho sub EE of t approaches 0, so rho sub EG of t is approaching 0, rho sub G E of t is approaching 0, rho sub GG of t is approaching 1. So what we could say here is rho of infinity equals this matrix, first row 0, 0, second row 0, 1. And that equals that ket G and then bra G. And the system decays to the ground state. All right, and for letter E, compute the von Neumann entropy as a function of time. So the von Neumann entropy is S of t equals negative trace rho of t ln rho of t. And for a 2x2 density matrix, its eigenvalues are lambda plus minus of t equals 1/2, and then we have bracket plus or minus, I'm sorry, bracket 1 plus or minus square root of quantity rho sub EE minus rho sub GG squared plus 4 times absolute value of rho sub EG squared. And from the above solutions, rho sub EE of t equals rho e to the negative gamma t, rho sub GG of t equals 1 minus rho e to the negative gamma t. So here the absolute value here of rho sub EG of t squared equals absolute value of rho sub EG of 0 squared e to the negative gamma t, where p equals rho sub EE of 0. So lambda plus minus of t equals 1/2 bracket 1 plus or minus the square root of quantity 2 p e to the negative gamma t minus 1, that squared, plus 4 times absolute value of 4 plus 4 times the absolute value of rho sub EG of 0 squared. That's a rho. And then e to the negative gamma t, all under the square root there. And then close bracket. Sorry about that. And S of t equals negative lambda plus of t ln lambda plus of t minus lambda minus of t ln lambda minus of t. So as t approaches 0, lambda plus approaches 1, lambda minus approaches 0. So S of infinity equals 0. And the final state in this situation happens to be pure. So that's all for this problem. Thank you very much and have a great day.